Hello, Professor. We are Group 19. Our project is Intelligent PV Module with AI-based maximum power plants, tracking and predictive control. I'm Zhuo Xianren, in charge of Part 1, Shao Jiewang for Part 2, Xin Tian for Part 3, Ying Xincao for Part 4, Chuan Aozhou for Part 5. We are divided into 5 parts. Part 1 is Limitations of Traditional MPPT. Part 2 is Traditional MPPT vs AI-based MPPT. Part 3 is AI-MPPT Architecture. Part 4 is Performance Comparison Expected Outcomes. Part 5 is Conclusions. Let's begin by looking at why traditional MPPT methods are no longer sufficient in real-world PV systems. Conventional MPPT algorithms such as perturb and observe or incremental conductance rely on simple rule-based logic, while easy to implement. These methods suffer from slow response and oscillations under fast-changing environmental conditions. As you can see in Figure A, the PO algorithm tends to oscillate around the maximum power point. This not only wastes energy but can also lead to tracking errors when the irradiance changes rapidly. Another major limitation occurs under partial shading. When different modules receive different levels of sunlight, the power voltage curve develops multiple peaks, as shown in Figure B. Traditional methods can easily get stuck at a local maximum, instead of finding the true global peak. This results in significant energy loss. Finally, most MPPT systems are centralized, treating the PV array as a single unit. This doesn't work well in distributed systems, where each module can behave differently due to shading, temperature, or aging. What we really need is a more intelligent and adaptive solution, one that can learn from data react in real time and optimize each module individually. To address this intelligence, we propose an AI-assisted MPPT controller that can overcome the limitations of rule-based logic. Let's take a look at how it works. Thank you.
So let us move to the part 2, the traditional MPPT versus the AI-based MPPT. So as we've just seen, the traditional MPPT methods like PO or incremental conductance struggle with slow response and oscillation when conditions change rapidly. So now let's watch a short clip that shows how an AI-enhanced MPPT system behaves in real time.
With lots of data on how factors like sunlight and temperature affect the solar panels. By analyzing this data, the AI learns to predict the best voltage and current settings for peak efficiency. The AI keeps checking the voltage and current from the panels. It then automatically adapts the settings to keep the panels operating at the point where they can generate the most power.
So based on that, you'll see how our AI-based MPPT replaces fixed rules with a neural network that learns from real data like the irradiance, temperature, voltage, and current to directly predict the optimal operating voltage. This delivers the faster convergence, minimal oscillation, and stronger adaptability under partial shading or sudden changes. And in this part, we present our 3-layer hybrid architecture designed to combine speed and stability. So in the learning layer, the ANN predicts output voltage's maximum power point. If an abrupt change or local peak occurs, the macro scan layer fine-tunes around the prediction. So if instability is detected, the safety fallback layer switches to the incremental conductance method to ensure reliable operation. The DC-DC converter then adjusts the duty cycle and sensor feedback closes the loop. So in summary, we are blending AI's predictive intelligence with traditional control robustness to enabling photovoltaic systems that are smarter, faster, and more stable.
Next, I'm going to talk about the AN model structure plus the input and output. Here you can see the architecture of my proposed AN-based MPPT controller. The goal is to predict the optimal MPP voltage directly from the environmental inputs. The inputs include solar irradiance, temperature, and PV voltage, while the output is either the predict VMPP or the DC-DC converter duty ratio. I use 3 hidden layers with IAL activation and train the network using data generated from MATLAB's PV model under different irradiance and temperature conditions. This allows the AN to replace the traditional perturb and observe logic with a much faster data-driven prediction. Now I'm going to talk about the MATLAB and Simulink plan. So this figure summarizes the workflow. First, a PV module is molded in Simscape. Then I collect the IVP data under multiple sunlight and temperature profiles. Next, the data is used to train a neural network in MATLAB. After training, the AN model is deployed as a controller block inside the Simulink, and finally, its performance compares with the traditional perturb and observe method in terms of efficiency, tracking speed, and stability. Now I'm showing you the complete Simulink implementation. On the left, we have the PV module and a whole boost converter circuit. At the top, you can see 2 controllers, which one is the PO controller and one is the AN controller. Both feeding into the same PID and converter, so we can directly compare their responses under identical conditions. This setup enables fair benchmarking between AI and conventional methods. Finally, on the left is the AN training code, which defines a simple feed-forward network with 3 fully connected layers, training using Adam Optimizer. On the right is the PO algorithm implemented in MATLAB function block. Compared to the iterative PO, the AN controller predicts the optimal duty ratio directly, achieving fast convergence and smaller oscillations near the MPPT, which it will be showed on the next stage.
Now let's look at how the AI-based MPPT actually performs compared to the traditional PO controller. This slide compares duty cycle responses. The traditional PNO controller adjusts gradually and oscillates around the optimal point. In contrast, the AI controller predicts the optimal duty in 1 step and converges almost instantly, achieving over 3 times faster dynamic responses. Moving on to power output, the traditional PNO reaches 130 watts in 0.03 seconds, while the AI controller hits 175 watts in just 0.02 seconds, a 35% boost in tracking efficiency and faster convergency. The next 2 plots shows the voltage and current responses. PNO shows strong rips at 7 to 8 volt and 15 amps, while AI control stabilize voltage at 8.5 volt and current at 18 amps, achieving smoother waveforms and more stable operation. Compared to the traditional PNO controller, the AI-based MPPT offers faster convergency, higher peak power, and reduced voltage and current rips, resulting in more stable operation, greater energy output, and improved system reliability.
To conclude, this project demonstrates how AI can significantly improve the performance of photovoltaic systems. Traditional MPPT algorithms like PNO and incremental conductance are simple but limited. They respond slowly and often oscillate around the maximum power point under changing sunlight. Our proposed AAN-based MPPT directly predicts the optimal MPP voltage from environmental and electrical inputs, enabling faster and smoother control. And what's more, in MATLAB and Simulink simulations, it achieved faster convergence, about 0.2 seconds and higher output power, increasing from 130 to 175 watts. Overall, this intelligent MPPT design improves tracking efficiency, stability, and energy yield, showing great potential for future smart solar systems. Thank you.